Hello and welcome back to Introductory Electromancy. Today we will be talking about Ohm's law and the power law. Very exciting. So, Ohm's law is probably the most important thing in electronics to remember, is V equals IR. I'm not sure where you are in algebra, dear viewer. I will attempt to explain this equation. So, equation is like a little scale. You could do the same thing to both sides of the equal sign, and it will remain true. You could, for example, double both sides. Or you could add 5 to both sides. You could divide and multiply both sides by any number. You cannot divide both sides by 0. But this right here, Ohm's law. This is, for whatever reason, the most common form of it. But say we divide both sides by r, you get V over R equals IR over R. Because the same thing is in the numerator and the denominator of the fraction, you can cancel them and get V over R equals I. This is the form that I find myself using the most in everyday life. Likewise, you could divide both sides by I, and then you would end up with V over I equals IR over I. These cancel because they are on the numerator and denominator of the fraction, and you get V over I equals R. So, Ohm's law, V equals IR, also V over R equals I, also V over I equals R. Before we get to the power law, let me explain what each of these numbers actually means. So V is voltage. It's measured in volts. I is current. Measured in amps. R is resistance. Measured in ohms. Why is I used for current? Because it was originally for intensity of current, intensité du courant, and it's kind of a funny thing. Basically, whenever any new field gets discovered, the people who come up with the symbols and notation for it don't understand it by definition because it's just been discovered. And so we end up with all of these weird quirks. But anyway, I is current in amps. Its symbol for the unit amps is A. The symbol for the unit volts is V. The symbol for the unit ohms is the Greek omega. And what do these things actually mean? So I'm going to be using the hydraulic analogy, which is masterfully executed in the Cartoon Guide to Physics. But if we imagine that our electrical circuit is actually a water circuit with some sort of pump instead of a battery that pumps water in a cycle through some piping, then voltage is equivalent to pressure. Amperage, amps, current, I, is equivalent to the rate of flow. And then resistance, R, is some sort of restriction. So volts, pressure, moment, amps, flow rate. Amperage, amps are a coulomb per second. A coulomb is just a really big number of electrons. So if a coulomb of electrons flow by a point in a second, then that is 1 amp of current. And then ohms would be opposition to flow. Now, in introductory electronics, they always tell you current has to flow in a closed loop, and if the loop is broken, current doesn't flow. That is how a switch works, for example, by opening the loop, which stops the flow of current through the whole thing. But it's not strictly true. You could, for example, say, this is the symbol for ground, if I can draw it. You could have a high-frequency alternating current source. This is the symbol for an alternating voltage source. You could attach it to a radio antenna. Now, if you do that, energy will be radiated from the antenna, and if you put something in line with it here, this thing would get power, even though there is not a closed circuit. But that is a special case that will not come up until later. All right, so we have Ohm's law. We've got 3 forms of it. Now, I'm going to also bring up the power law. Power law is P equals IV. Power equals current times voltage. Power is measured in watts. you might find, for example, in the last millennium, the one that I'm from, the one with the Marco Polo and Genghis Khan. Anyway, a 100-watt light bulb. The light bulb is rated in terms of how much power it dissipates. Now, given that we have this equation and these ones, we can use substitution to convert the power law into different forms. So, P equals IV. Well, I equals V over R. So, P equals V over R times V, which simplifies to P equals V squared over R. This is an alternate and valid form of the power law. Likewise, we can substitute for V. P equals IV, well, V equals IR. So P equals I times IR. So P equals I squared R. This form of the power law is important because it indicates that power dissipation is proportional to the resistance times the current squared. This equation is the reason that we have high voltage transformers for a power line. So you have your electrical generating station. Then it is sent to a transformer. And then through high voltage power lines. Then, before it goes into your house, goes through another transformer. The advantage of this is that you can convert it to a very high voltage, which means that you don't need to carry as much current on these power lines. And reducing the current reduces the power dissipation because of this equation. However, because the total power is current times voltage, if you double the voltage and cut the current in half, the amount stays the same. So this is the reason that you see all of those little transformers attached to power poles or underground if you're in Europe. They convert the high voltage of the transmission line down to the 120 or 220 or 240 volts that your house uses, depending on where you are. So this is rather a lot of math. I mean, it all fits in one page, but still rather a lot. Now for practical application, we will be meeting our friend, the multimeter. This is our friend, the multimeter. This is a pretty common type. You can get a wide variety of different multimeters. Many of them will look like this. Less expensive ones will not generally have this on-off switch. Instead, the top position will be off. But you can see it's split into sections depending on what you want to measure. DC voltage, the omega symbol for resistance. This one has a diode test function, and HFE, also known as beta, which is gain of transistors. We'll skip over that for the time being. And this we will skip over for the time being. Then current. You can measure DC amps up to 200 milliamps. If you want to measure more than that, you have to move the red lead to this socket, which connects it to the 10 amp reading section. You can also measure AC voltage up to a maximum of 200 or 750 volts. There are a variety of ways that you, dear viewer, can destroy your multimeter. Not that you should want to, but it might happen by accident. So if you have it set to measure DC voltage, the multimeter acts like a high-value resistor. Ideally, it should have infinite input impedance, but this is the real world, which is very infrequently ideal. It's generally pretty safe to go poking random circuits in random states of power if you have it set to measure voltage. But if you set the meter to measure current, what it does is run a small current through the thing that you're testing. Or, well, yes, but it applies a small voltage across the thing you're testing, then measures the resultant current, then does the math to figure out what resistance that would correspond to. So, if you set it to ohms, the meter itself will actually output a few fractions of a volt and use the resulting current to measure the resistance that it's connected to. Because it's meant to only output a few fractions of a volt, if you set it to ohms and then connect it to something that's powered on, forcing the voltage back across the meter, then you can damage it. Now, the most spectacular way to damage your meter is with the amperage measuring settings. If you set your meter to measure amps, then the meter acts like a very small resistance, ideally a resistance of 0, because to measure amps, you put the meter in line with the circuit that you're measuring to measure the flow around it. And so if you set your meter to measure amps and then put it across a voltage source like a battery or the wall outlet, then it will act like a short circuit through your meter, destroying it. Now, in this settings range, there will be an internal fuse that'll pop if you do that. If you set it to 10 amps, then you can really start some interesting fires by shorting whatever you're measuring through the meter. So don't leave your meter set to measure amps and then try to measure voltage with it. You'll have a bad time. Now for practical application, let's measure some things. I have this same circuit that we worked on previously, 1 kilo ohm resistor, LED, switch, battery, 2 output leads. Let's start by measuring the voltage of our battery. This is a 9-volt battery, so we want to use the range that goes above that. Any of these would work. 20 volts, 200 volts, 1000 volts, because they are all bigger than 9 volts. We'll get the most precise result using the one that is just above what we are measuring. So we do this, we connect it, and it measures negative 8.56 volts. Why is it negative? It's negative because this is actually the negative output terminal of the battery. If you connect it backwards, as I'm doing, you get a negative result. Guess what? We can just switch the polarity of the battery, and wow, we get a positive result. This is to be expected. It's the same number either way. And if you're just testing batteries with it, it doesn't really matter which way you connect it, as long as you remember that you can take the absolute value of the result. Now let's measure a resistance. This resistor is supposed to be 1000 ohms, because it is labeled with the color code brown, black, red, gold, 1000 ohms plus or minus 5%. So 1000 ohms The value that goes above that but is the closest is the 2000 ohm measuring setting. Let's see if I can prop my phone up on this roll of solder. I can. Great. So now I'm making sure the circuit is powered down. You can measure across the resistor 994 ohms, looks like, which is about right. So it's 6 ohms too low. Let me see if I can get the multimeter more visible. Oh, well, that makes it entirely invisible. That's better. $993 ohms. It's normal for these values to vary a little bit. It depends on how well I'm pressing these points into the leads themselves, because a bigger area of contact gives you a lower resistance, and if it's just barely touching, you'll get a higher resistance reading. So this resistor is indeed about 1,000 ohms. Another thing to note is that normally you can't measure resistors in the circuit like this because there will be other circuit elements that are also in parallel with it. We'll get into series and parallel circuits later, but suffice it to say, if there's a second resistor somewhere on this board that's connected across this one in parallel, you won't be able to measure this one directly because you'll be measuring the combination of the two. In this case, since one lead of the resistor goes to a completely open circuit, you can measure it while it is soldered to the board and get an accurate reading. So now let me get a handy dandy clip lead from my pile of clip leads. We're going to start looking at this in more detail. I am glossing over the voltage lost in the LED at the moment. We'll get into it in more detail later. But let's power this thing on. And then we're going to use the multimeter to measure the current flow through it. Conventional current coming out the positive lead, going into the negative lead. So we set our multimeter to measure milliamps. The actual milliamp value should be about 6.97, something like that. We'll see shortly. Now to measure current with a multimeter, we're going to run the current through the meter itself. This is how you get into trouble trying to use it, leaving it in current mode and then putting it across a battery. So output from the positive lead, input to the negative lead, and it looks like 5.7 to 5.9 is our actual output current value. Oh, 6.0. 6.1. Let's call it 6.2. Now we're getting up to 6.3. All right, fine. 6.3 milliamps. Just going to write that down somewhere. Little m, big A, little m means milli, means thousandths, like millimeters. So 6.3 milliamps. We measured our resistor at 994 ohms, let's call it that. Now what should the voltage across the resistor be? Well, since V equals IR, and we know I, we know R, V equals 0.0063 amps times 994 ohms, which in this case will be about equal to 6.3 volts. So let's measure it and see if that is actually accurate. So for this test, we're going to short the continuity tester we have built and then measure the voltage across the resistor with the device running. So we set this to volts. Poke the resistor. And we get a measurement of 6.33 volts. Pretty close to 6.3. Hey, Ohm's law is accurate. Go figure. Now what's the power dissipated in the resistor? Well, power equals voltage times current. So the power in watts will be equal to 0.0063 times the voltage, which is 6.33 volts. So about 40 milliwatts. This is a half-watt resistor, so it would be rated for 500 milliwatts. So we are well within the safe operating region. It's recommended to run all your components at half their rated power. This is called derating, and it's a good idea in general because it'll make everything you build more reliable at the expense of using larger and more expensive parts. But in the case of a single resistor, it does not matter that much. Alrighty. Well, that's all for today. I will be back at it in the future. Have fun, everyone.